Hello everyone, this is Professor Robert Solis. Welcome to this next video lesson. We're going to continue talking about the assembly language, and what I'm going to do is show you a very simple program that allows us to add numbers, subtract numbers, multiply and divide numbers, and also modulus as well, using the inline assembly language approach. So the first thing that I'm going to do is I'm going to create several variables, num1, num2, and this will be the result. The user operator will be either addition, subtraction, multiplication, and so I'm going to obtain those values via cout and cin statements. And then as you can see over here, I have a switch statement that is going to obtain what the user entered. So if the user entered a plus symbol like this, obviously they mean addition. If the user entered a hyphen like this, that means subtraction. Now the user could enter X or the asterisk, which is more commonly known for multiplication, but amongst mathematics majors, they might enter an X, which of course means multiplication. And then modulus, typically in object-oriented programming languages, the percent symbol is used as the modulus operator. And then of course for division, we have the /. So again, we have a switch statement to go to those specific case locations. And then within there, we have an inline assembly program that's going to take care of each of these different operations. So what we want to do is to stop at each of the different locations and see what happens. So let me go ahead and stop right here, and we're going to do addition first, I should say. So let me go ahead and run this program, and it says enter a number. And so let me move this over here, right? So we're going to enter a number, and let's say that I enter 5, enter, I enter 2, enter. What is the operator? And in this case, I'm going to hit or enter the plus symbol, and then press enter. And you can see here that we've stopped the program at this point. So notice that I have my registers open. I also have the flags available. I can just simply right-click over here, and I selected flags so that I can see what it is that that's happening. I also could take a look at the various registers. All right, so what we're about to do is to take the number 5 and move that into the EAX register. So if I step over, notice that the EAX register is now equal to the number 5. Into the EBX register, I'm going to move the number 2. So let me step, and so the EBX register now has the number 2. Now, if you're going to add two numbers together, if you're going to add two registers together, you would use this add assembly language keyword, and then what happens is you include the two registers that you're going to add. The result of the addition of these two registers is placed right back into the EAX register. So as you can see here, EAX is 5. We are about to add 5 plus 2, and the answer goes right back into the EAX register. So this is going to get lost. Now, of course, that value is still in num1, but the value of the EAX register has been updated, so to speak. So when I step through, notice over here, the EAX register is now 7. All right, well, now what I want to do is I created a variable over here called result, and what I want to do is I want to move the contents of the EAX register and move that into result. All right, so if I were to step through this, notice that over here, the move has taken place, result is now 7, and so now I'm going to step and I'm going to simply output the following, where I indicate to the user that 5 plus 2 is equal to 7. All right, so let's do this again. We're going to stop the code. I'm going to enter 5, I'm going to enter 2, and the plus symbol. All right, we're stopping the code right here. Moving to the EAX, moving to the EBX register. Okay, that's fine. Let's dive into this in terms of what happens to the flags. So let me go ahead and add this, and so you'll notice that I have these two flags that have now activated. So the CY flag, it says 0, and the PL flag, it says 0. Now the PL flag, that's basically the sign flag. It's indicating what the sign of the number is, and in this case we're just simply saying that the sign is that there is no sign. It's positive. If it did have a number 1 over here, that would indicate that this is a negative number. And then there was no carry, so that's why we see the 0 over here, and all the other flags weren't affected by this add operation. All right, so that's why we're simply able to take this and move it over here. Okay, no big deal. Let's see what happens here if I deal with subtraction. So let me go ahead and stop the program, and instead of breaking here, I'm going to break right over here. Actually, you know what I could do is just simply break right here at the switch statement, and then it'll go to the appropriate portion once I step into it. So let me go ahead and run the program, and I'll do this. First I'll do 5 minus 2, and then we'll do 2 minus 5 and see what happens. So I'll say 5, enter, 2, enter, and the operator is subtraction or minus. So let me go ahead and press enter. And we're stopping the program right here. Let me go ahead and step. And so as you can see here, it goes to this case because I entered minus or subtraction. And so what are we going to do? We're going to move the number, which is 5. We're going to move 2 into EBX. We're going to move 5 into EAX. So if I step and if I step, you can see now the value of EAX and the value of EBX. All right, so for the subtraction of two numbers or two registers, we use sub. Sub is going to subtract two registers. And what it'll do is it'll put the results of the subtraction right back into the EAX register. So over here you see hexadecimal 5, you see hexadecimal 2. All right, so if I step through this, 5 minus 2 is 3, and so that's why you see the 3 over there. Now before I move on, let's see what happens. It says that the carry is 0. It says that the parity, PE means is the parity even, and this one is saying, yeah, there's an even number of ones. And then it says in terms of the sign, that's 0. So let's see here. What happens if I have, what did we enter? We entered 5 and we entered 2. We're subtracting those. So let me go over here to my graphics program over here. And let's see here. We have 5, which is this number right here. And we have 2, which is this number right here. And we're going to subtract those. All right, so if I subtract those, remember this is really 5 minus, did I say 5 minus 2? I keep on forgetting here. 5 and 2. Yes, I said 5 minus 2. All right, so 1, 2, 4, that's 5, and then 0, this is 1 rather, and 2, so this is the number 2. And we know that this is going to be 3, but how do we represent that in binary? All right, so 1 minus 0, easy, that's 1. Can't do 0 minus 1, so I have to borrow, so this goes to 0, this goes to 1. So 1, 0 is the same thing as binary 2. 2 minus 1 is 1. All right, how many ones do we have? Do we have an odd number, or do we have an even number of ones? Well, in this case, you can see that I have 2 ones, and that is an even number, which is exactly why this is showing PE is equal to 1. We have an even, the result is an even number of ones. And so that's what that flag means. Do we have a carry? Did a carry take place? No. Is the sign negative? No. The 0 indicates that the sign is positive. All right, so then what we're about to do is we're about to take the value inside of EAX and put that into result. So now result is equal to 3. And then if I continue the program, it's going to simply show that 5 minus 2 is equal to 3. Okay, so pretty easy. Let's run this program again. We did 5 minus 2. What about 2 minus 5? What happens there? So the answer, of course, is negative 3, but let's see what happens when I'm running this program over here. So it looks like I'm going to step to the appropriate case. We're going to move the numbers into the registers. So register EAX has 2, register EBX has 5, because that's what we did over here. And now we're going to subtract those two. So let me just step, and now let's see what happens. So I get some crazy looking number over here, and it looks like it says auxiliary carry is 1. Well, what happened here? Well, let's go back over here to my graphics program, and let's see if I can explain what's going on here. So first of all, we said, what is 2 minus 5? And of course, you know that the answer to this is negative 3. Now, your elementary school teacher probably taught you what you do is you take the larger number, and then the number that has the larger number has the sign. That's what the answer is going to be. So 5 over here is the larger number. It has a negative sign, so the answer is going to be negative. And then you just simply said, okay, what's 5 minus 2? That's 3, and so that's probably how you worked it out when you were a little kid. Well, inside of a computer, how do we do this? Okay, so first of all, let's represent this number, which is a positive number, right? So I'll put a plus over here, although you don't typically put a plus symbol over here, but that is a positive number. And so that's going to be 1, 0 in binary. Now this number over here is the number 5, right? Okay, so I'm going to put a 1 0 and a 1, right? Because that's 1, 2, 4, right? 4 plus 1 is 5. That's this number is 5. And what we're doing is we're trying to subtract this from this. All right, well, you can't do that when you're dealing with binary numbers. You don't subtract numbers like this. Instead, what we have to do is we have to convert the negative number into its 2's complement. And we have to do this within a certain number of bits. So what I'm going to do is I'm going to convert all these into 4-bit numbers. Watch how I do that. So I just simply put a 0 over here, a 0 over here, and a 0 over here. Why a 4-bit number? Because this is referred to as a nibble. And 2 nibbles is equal to a byte, which is an 8-bit number. And 2 8-bit numbers is a 16-bit number, and so forth and so on. All right, so what I do is I try to convert this, or not, represent it, I should say, not convert it. Represent it as either 4 bits or 8 bits or 16 bits, so forth and so on. All right, so if that's the case, first of all, let me rewrite the positive number, which is nothing more than this, 0, 0, 1, 0. That's the number 2. And then over here, this negative number, let me deal with this over here. So that's going to be 0, 1, 0, 1. Let's change this into the 1's complement. Well, the 1's complement, you just simply invert the bits. So that's going to be 1, 0, 1, 0. Then we're going to represent this as the 2's complement. The 2's complement is you add 1 to the 1's complement. So over here, I'm about to add 1 to this number. Well, if that's the case, 0 plus 1 is 1. The 1 plus the 0 over here is 1. The 0 plus 0 is 0. The 1 plus 0 is 1. Whoops, sorry, is 1. Okay, so this number right here, negative 5, is really this number in its 2 complement, and we add the 2's complement. So this is going to be this. This is the 2's complement of negative 5, and we add that. So now what we get is this. Let's see, 0 plus 1 is 1. 1 plus 1 is 2. So that means I put the 0 down and I carry the 1 over here because 1, 0 is 2. 1 plus 0 plus 0, that's 1. 0 plus 1, that's 1. Okay, so first of all, here's something to notice. If that high bit is a 1, then we know that the answer is negative. So, okay, we can put a negative right here. We know the answer is negative. All right. So when I convert this back from its 2's complement, then I'll know that it's negative because that 1 right there. Now, if that were 0, then the answer would be positive. All right, so let's take this. I'm going to move this over here, and let's rewrite this. So that's 1, 1, 0, 1. I'm going to do the 1's complement, which is 0, 0, 1, 0. In other words, I'm flipping all the bits. And then I'm going to add 1 to this. So I'll go over here and add 1 to it. And so that's going to be what? 0 plus 1 is 1. 1 plus 0 is 1. And then, of course, this is 0. This is 0. Well, what is this? This is 1 plus 2. Let me see. 1, 2, 4, 8. But only the 1 and the 2 flag, or the 1 and the 2 bits are on. So that's going to equal to decimal 3. So in other words, this is equal to negative 3. And we know that because 2 minus 3 is, in fact, negative 3. But what I'm showing you is how we did this using the 2's complement, which is exactly what's happening over here with our program. So why did this auxiliary carry activate? Well, the reason why it activated is, in other words, AC, or auxiliary carry, is asking the question, did a carry take place within the first 4 bits? Because if it did, we're going to set this flag. And as you can see, a carry did take place. Here it is. Right? A carry did take place because that's what AC does. It's asking if an auxiliary carry took place within the first 4 bits. Now, if a carry took place within the total of the 8 bits, then we would see this right here, where we would see carry is equal to 1. So that's how this works out. In this case, we subtracted a larger number from a smaller number, and so we're getting this. Now we're about to move the EAX register into result, and so that's why we see over here that result is negative 3. And then if I were to continue the program, you can see that 2 minus 5 is in fact equal to negative 3. Okay, so that takes care of how to add numbers and how to subtract numbers. Let's deal with multiplication. Now really, this is just two of the same sets of code. We don't know if the user is going to enter X or if they're going to enter the asterisk to represent multiplication. All right, so let's see what happens if I run a program here that says what is 4 times 2, and I'll just use the asterisk, right? So this is really going to multiply 4 times 2, which of course is 8. Let's see what happens. So now I'm going to step, and as you can see, it takes me right to this appropriate case where I have an inline assembly program. Well, first I'm going to move into the EAX register the number 4. Okay, so let's see here. Up there's the number 4. And then I'm going to move into the EBX register the number 2. All right, there it is. Now, when you're using MUL, which is going to multiply two numbers together, what it's going to do is it's going to say, okay, what is the number in the EAX register times, and then you tell it what register you're going to multiply it by, which in this case, the number that we're going to multiply it by is in the EBX register. So when I step through this, notice what happens. The EAX register gets updated. So MUL is a little bit different than sub, for example, because in sub you need these two parameters. You're going to take this minus this, and you're putting the answer right back over here. Well, for MUL, it doesn't work like that. The answer is automatically going to be placed into the EAX register. The question is, what are you multiplying the EAX register times? And so what this does is it says, okay, take the EAX register and multiply times EBX, and put the answer right back into the EAX register. And that's what, in fact, has taken place here. Remember, this used to be 4. 4 times 2 is 8, and so it puts the answer right back here into the EAX register. What is the sign? The sign is positive. If this were a 1, that would indicate that the sign is negative. Okay, what is the parity? Well, notice over here that it's 0, and the reason, let's see here, let's take a look. So what do we have here when we represent the number 8? So that's going to be 1, 2, 4, 8, right? So this is, pretend there's a 1, 2, 4, 8. This is in the 8th position. How many 1s do I have here? Well, it looks like I have 1, 1, and so that's an odd number of 1s. And that's why you see, is this thing parity even? No, it's not parity even. It's parity odd. That's why you see that as 0. Did any carry take place? No, we have no carry that took place. All right, so now what we're going to do is we're going to take the result of this, and this is what we'll do. We'll take EAX, which has the number 8. We'll put it into the variable result. And so now you can see that result has the variable 8. And now we just simply run the program. 4 times 2 is equal to 8. Right? So if you want to multiply two numbers together, you're going to use MUL. It's a little bit different than sub. It's a little bit different than add in that you don't do this. You don't put MUL EAX, comma, EBX. No. It's assumed that you are going to be multiplying the number times EAX, the number that's in that register. The question is, what's the other register that you want to multiply it by? And that's how that works out. Okay? So both of these pretty much do the same thing. How about modulus? Let's consider modulus. So remember, modulus is find what the remainder is. So let's go ahead and say I have the number 5 over here and the number 2 over here, and I'm going to put the percent symbol. So what I'm asking for is, what is the remainder of 5 divided by 2? Well, 5 divided by 2 is 2 with a remainder of 1. So let's see what happens here. So I'm going to jump to the appropriate location. Sure enough, here it is. I have an inline assembly program here. Let's go ahead and move the various numbers into the EAX and EBX register. So I'm going to step through that. Okay, here we go. All right, so the way this works out is as follows. First of all, we are going to, so you see over here EAX has 5, EBX has 2. So what I'm going to do is I'm going to say IDIV, and what IDIV does is it performs a division of whatever's in the EAX register divided by, well, whatever other register you're interested in. I could have used ECX. Say, for example, I used EBX. So in essence, what this is going to do is say, what is the division of 5 divided by 2, or EAX divided by EBX? All right, so we do that, so we step through that, and now the next, so the first thing you notice is that EAX says 2, and that makes sense. 5 divided by 2 is integer 2. But remember, I'm interested in the quotient. I'm interested rather in the remainder. So you'll notice over here, this EBX register, it has the number 1. See, here's how IDIV works. The way that IDIV works is that the quotient is going to be placed into EAX, and the remainder is going to be placed into the EBX register. So sure enough, 5 divided by 2 is 2, and the remainder is in the EBX register, which is 1. By the way, in assembly, if you want to write a comment, this is how you do it. See that semicolon right there? See, in C++, you do this, slash, slash, and that's a comment. Well, in assembly, you put a quote, a semicolon, and then everything after that semicolon is considered a comment. And so I'm just writing a comment here to remind me the quotient for IDIV, the quotient is placed into the EAX register, and then the remainder is placed into the EDX register. So that's why I'm going to take that EDX register and send it to the result, and I'm going to send result to the screen so I can see what the modulus is. So 5 mod 2 is equal to 1. All right. Let's try the modulus one more time. Let's say that I have an even number like 10, and I'm going to mod that with the number 2. So in other words, this is asking what is the division of 10 divided by 2, or what is the remainder, I should say, of 10 divided by 2. That's what 10 mod 2 means. Well, it should be 0, right? Because that's an even number divided by 2, so it should be 0. So let's see what happens if I step. So again, I'm going to move both numbers into the EAX and EBX register. Now it says A there because this is a hexadecimal representation, and A means 10. EBX has 2, okay, so this is going to basically divide 10 times 10 divided by 2, place the answer into EAX, and then place the remainder into EDX. So let's see what happens when I step. 10 divided by 2 is 5. EDX, well, it's 0. There is no remainder, and that's exactly what you would expect. The remainder of 10 mod 2 is 0. There is no remainder. Okay, so that's pretty cool. That's how that's how IDIV works. It's splitting up the answer. Here's where the quotient goes. Here's where the remainder goes. All right, and then finally, let's take a look at division. Let's see how this works. All right, so let me go ahead and run my program, and let's say, what is 10 divided by 2? Something very simple, right? And I'm going to put the slash right here. So let me just go ahead and run it first so I can show you what it looks like. So I'll just say continue. And let's see, it says 10 divided by 2 is equal to 5. Well, that's correct. So how did you do it in assembly language? Well, let's do this again. So 10, 5, and the division symbol. All right, so we've stopped over here at the switch. Now it's going to jump over here to that particular case where we have an inline assembly program. And so it looks like I'm using exclusive OR. Now, if you recall an exclusive OR, the truth table says that if both the inputs are different, then the output is true. If both the inputs are the same, then the output is false. That's how the exclusive OR works. So it looks like I'm doing this. It looks like I'm taking EDX and I'm exclusive ORing it with EDX. Well, let's see here. What's in this? Okay, so it looks like EDX has this number right here. So let's see here. If I go over here and say 10, so that's, let me see here, that's 1, 2, 4, 8, and I want to make 10 from that, so that means this bit and this bit over here are going to be activated. So 10 is really 1, 0, 1, 0 in terms of a binary number, right? Now, if I exclusive OR that, so let's take this over here, and I'm going to rewrite this number over here right below it, and I'm going to exclusive OR it. And remember, the truth table, let me just write this really quickly over here. So I have X, Y, and let's say that I want to do exclusive OR of that. And typically exclusive OR is the plus symbol with the circle around it. All right, and of course I have all these options. I have 0, 1, 2, and 3. All right. Anytime that the bits are the same, the answer is false. Anytime that the bits or the inputs are different, then the output is true. Notice over here, if I exclusive OR these two, right? If I exclusive OR these two, what is the answer? Okay, bits are the same, 0. 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 So isn't this interesting? What does exclusive OR do? It clears. Look at this, it clears. So if I go back over here, do you now know what I'm doing to the EDX register? I'm clearing it. When I exclusive OR EDX by EDX, what happens? It's going to clear. So do you see the EDX register? It has A in there. Now when I step through, now notice it's cleared. It's all 0. Now, Why do I do this? I bet you I'm going to be using the EDX register for something, and in fact, what do I use it for? The remainder. Okay, so let's see what happens. Now I'm going to move num1 into EAX, num2 into EDX. Okay, so that's pretty standard. We've seen that before. Here's the number 10. Here's the number 5. So we're basically saying, what is 10 divided by 5? And of course, the answer is 2. So I'm going to use IDIV. Well, that's very similar to what I did for modulus, right? I'm using IDIV. But the reason why I cleared the EDX register was because I'm going to be using that. That's going to hold the remainder if there is, in fact, a remainder. So let me go ahead and activate IDIV, and you know that this is really going to divide EAX divided by EBX. Well, EAX, which was 10, divided by 5, the answer is 2, so that's why we see 2 here. And so the EAX register is 2. What's the remainder? Let's see here. So if I go to the EDX register, the remainder is 0, and that makes sense. Right? There is no remainder of 10 divided by 5. And so now if I were to continue over here, what is 10 divided by 5? It's 2. All right, let's see if we can generate something with a remainder. So let me run the program again, and I'll say 5, 2, and divide. I want to divide those two. So what is 5 divided by 2? Well, 5 divided by 2 is 2 with a remainder of 1. So let's see how that works out. So I step into the appropriate case. The first thing that I'm going to do is to clear that EDX register just to make sure that it's cleared, because that will hold the remainder. And if there's something in there, well, that's not good. So I got to get rid of the stuff that's in there. So you've learned now that if you want to clear a register, you just simply exclusive OR it by itself. And so watch what happens. EDX register is now blanked. Beautiful. Now I can go ahead and move num1 into EAX, num2 into EBX, and here it is. Here's 5, here's 2. So I'm asking, what is the division of 5 divided by 2? Now, what I'll do is I'll use IDIV, which really means what is EAX divided by EBX? Okay, so what's the answer? Well, the answer is 2. Look at this. The EDX register has the number 1 here. So you know that what IDIV does is it places the quotient in EAX, and it places the remainder in EDX. So that's why I'm going to say, okay, so what is the result? Well, remember, in this case, I really do want the number 2. Right? But just know that the remainder is placed over here in EDX. So when I continue, what is 5 divided by 2? Integer, well, it's 2. And of course, I think you've already been able to surmise that IDIV is an integer division. That's why we want to know what the remainder is, right? So we have the quotient over here in EAX. We have the remainder here in EDX. All right, so this is a really simple little program that shows you how to use arithmetic operators in the assembly language. This is add, sub, we have MUL, we have MUL over here again because I don't know if the user is going to enter this or this. We have modulus. Well, there really is no modulus. Instead, what we do for modulus is we use IDIV because we know how IDIV works now. IDIV places the quotient in EAX, IDIV places the remainder in EDX. So in this case, the modulus really is, well, what's the remainder? Well, that's in EDX. So let's output whatever is in EDX into this variable. Now for regular division, we know that the quotient is in EAX, which is why I did move result EAX into result. And then I'm going to go ahead and display whatever the result is. And that's it. So this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.